We are going to look at how to interpret graphs of rational functions. We're going to spend 2 days looking at different types of asymptotes and how you find them. For the warm-up, give your definition of a rational function. So we've talked about this for the last few days. A good definition, you could say it's the ratio of two polynomials. Simplify the following. We've learned to simplify. You're going to factor and you're going to cancel the ones. So the first part, you can use a box and circle, or think what multiplies to -4 that adds to 2. So we would have x plus 6, x minus 4. In the denominator, it's difference of squares. And if you take the square root of x squared as x, the square root of 16 is 4. So you'd have x plus 4, x minus 4. Cancel any ones. So the simplified form is x plus 6 over x plus 4. For the next one, notice the numerator has an x in each term, so factor that out first. You're left with x squared plus 10x plus 21. On the bottom, you can factor out a 2x. When you do so, you're left with x plus 7. You can use a box and circle to factor the remaining part, or the trinomial on the top. Or think what multiplies to 21 that adds to 10, and that would be x plus 7, x plus 3. On the bottom we have 2x, x plus 7. Cancel any ones. In this case, it would be the x plus 7s, the x's, and it looks like that's it. So we're left with x plus 3 over 2. And there's the factored form, simplified form. We looked at asymptotes yesterday, so to review, an asymptote is a line that a curve approaches as it heads towards infinity. So here's an example. The blue line would represent the curve. You can see that as it heads towards infinity, the curve approaches that line, but it never crosses it. Yesterday we explored two types of asymptotes, a horizontal asymptote and a vertical asymptote. Here was the parent function we've been looking at the last several days. Y equals 1 over x. And if we draw in the asymptotes, usually they're dashed lines because they don't really exist in the graph. So the first one would be this vertical asymptote. And that vertical asymptote has an equation of x equals 0. There's also a horizontal asymptote. So that horizontal asymptote would be y equals 0. Again, y equals 0 because all along this line y equals 0, or in other words, the y-intercept is 0 and the slope is 0. The vertical is x equals 0 because, again, all along that line x is 0. We've looked at this function before, the shifted function. F of x equals 1 over x minus 2. Draw and label the asymptotes. We knew from our investigation yesterday that the x minus 2 shifts the function to the right 2. So think about what asymptote that affects. It affects the vertical asymptote. So our horizontal asymptote remains the same, but right 2, instead of being at x equals 0, we're going to shift that asymptote right 2, and then we can redraw our function. So here's a sketch of the function. So make your shift and then draw on the asymptotes. Again, this one shifts to x equals 2. This is y equals 0. Do an investigation day looking for vertical asymptotes. Using your graphing calculator, find the vertical asymptotes of each rational function. All the while you should be thinking, why do vertical asymptotes exist? How are they found? Just by looking at the function. So if we pull up our calculator, you can predict what this is going to do. X plus 2 would be left 2, but if we pull up our calculator, we have 1 divided by parentheses, x plus 2. And again, you can see that the horizontal has asymptote stays the same, y equals 0. The vertical goes 2 to the left as we predicted. And if we write just the vertical asymptote, x equals -2. Try the next one, 1 over x minus 3, x plus 2. What happens there? So I'm going to press tab, go up, and on the bottom here, oops, I'll put this in parentheses again. And then I'll add in, whoops, I think that's right. Oop, nope, I don't want that. Okay, there we go. and I think it was x minus 3. So let's see what happens if we add in that x minus 3 on the bottom. Hit enter. Oh look, it looks like there's two asymptotes. One at x equals 3 and one at x equals negative 2. So again, we have the x equals negative 2. And now we have a new one at x equals 3. Let's try the next one, x plus 4, x plus 1 on the bottom. So again, hit tab, go up. So again, it was x plus 4, x plus 1. You can make a prediction of what you think is going to happen. Hit enter. Did your prediction hold true? There's an asymptote at x equals negative 1 and at x equals negative 4. Try the last one, 1 over x times x minus 5, x plus 3. Okay, so hit tab, go up. So I'm going to put an x right here. And it was x minus 5 and x plus 3. Make a prediction. Okay, I guess it's not going to graph it for us. Maybe if I put a parentheses around it, well. Okay, well I guess I'll explain what happens then. For this one, we'll have an asymptote at x equals 0, x equals 5, and x equals negative 3. So look for a pattern here. How can you tell just by looking at the function what the horizontal or the vertical asymptote is going to be? If you've noticed, the vertical asymptote is the 0. It's the opposite of the factor. So what is the 0 of x plus 2? It's x equals negative 2. What makes x minus 3 0? A 3. What makes x plus 2 0? A negative 2. What makes x plus 1 0? A negative 1. What makes x plus 4 0? A negative 4. What makes x 0? 0. What makes x minus 5 0? 5. And what makes x plus 3 0? A negative 3. How are asymptotes found? By just looking at the function. So you have to look at the factored form. And it's what makes each factor equal 0. It's the zeros of the bottom. Why do vertical asymptotes exist? Well, think about it. Can we divide by 0? And we can. It's undefined. So division by 0 is undefined. So there's no graph there. If there's ever anything that makes the bottom 0, we can't have a graph there because it's undefined. So an asymptote exists. Make a prediction. What are the vertical asymptotes of 1 over x minus 9, x plus 8? That would be at x equals 9, x equals negative 8. All right, so to review, how to find a vertical asymptote. Set the denominator equal to 0 and solve. This is like finding the bad spots in the domain. It's where the function cannot exist. So here's the first example. Let's factor it first. You do need a factor. So the top would factor to what multiplies to negative 6 adds to negative 1, x minus 3, x plus 2. On the bottom, it's difference of squares, x plus 1, x minus 1. So once you have it factored and you've canceled the ones, you look at the bottom. What makes this 0? X equals negative 1. What makes this 0? X equals 1. So there's two asymptotes, two vertical asymptotes at negative 1 and 1. You try this one. Top is already factored. X minus 3, can you factor the bottom? And if you do so, what multiplies to negative 10 that adds to negative 3? That would be negative 5, x minus 5, x plus 2. Cancel any ones. Here there's none, so you take a look at the bottom. What would make this 0? 5. What would make x plus 2 0? Negative 2. So a graph cannot exist in either of those places because division by 2 is undefined, so you have vertical asymptotes. One more thing we'll look at today is called a hole in the graph. And this happens when you have the same factor on the top and the bottom. A hole or point of discontinuity will exist in the graph when both the numerator and denominator equals 0. How do we tell where the holes are? You factor. You look for the same factor in the numerator and denominator. A hole exists where this factor is 0. Here's your example. We have x plus 5 over x squared plus 8x plus 15. Factor. X plus 5 is already factored. What multiplies to 15 and adds to 8? That would be x plus 5, x plus 3. All right, we take a look at the factors that are the same, these would cancel. So there would be a hole in the graph there, and the hole would be what makes this 0. So the hole would be at -5, not at 5, but what makes that factor 0. There would also be an asymptote here, and that's the next question. The asymptote would be then just the remaining factor, what makes this 0. So the asymptote, the vertical asymptote, will be x equals -3. So there's a graph below. You can see the hole at -5. You can see the asymptote at -3. So I'll sketch that in. Here's a asymptote at x equals -3. So today you should feel comfortable doing the following. Factor the polynomials. We've practiced factoring quite a bit. Locating and writing the equations for vertical asymptotes. Again, vertical will be x equals. And also locating the holes. So factor the top and bottom. If you have the same factor, what would make that 0? Tomorrow we're going to look at the other type of asymptote. How do you find horizontal asymptotes? Your assignment is 8-7, day 1 worksheet.